Okay, this is a short lecture on centripetal acceleration and centripetal force. Centripetal acceleration is the acceleration that comes as an object is moving at a uniform speed around a circle. So as that object is moving around a circle, even if it's at a constant speed, it will never be at a constant velocity because it's always changing direction. Right? And so even if this speed doesn't change, that direction is going to be causing an acceleration. If you change your velocity over a period of time, that's the definition of acceleration. So the equation that you end up with is this. Centripetal acceleration is equal to v squared divided by the velocity squared divided by the radius of the circle that the turn is happening in. Now, that equation is derived from a combination of the triangle that is created from the circle, the radius, the angle, and the arc, and it's also derived from that triangle's similarity to a triangle that is created when you add these two vectors together, to two velocity vectors together, and you get their resultant. They're similar triangles, and through some abracaphysics, you're going to end up with this equation, which shows us that as you go around the circle, there's an acceleration pointing in. And it's going to happen all the way around, because as the velocity vectors change, remember the speed's not changing, but as the direction of those velocity vectors changes, the proportion of the change in velocity is always going to be the same. So every time, every combination of vectors that you're going to use, all right, is going to give you a centripetal acceleration pointing into the center. So when you have a special kind of acceleration, well, that means that you're going to have a special kind of force. That special kind of force is called centripetal force. And I want to be clear that, notice I'm putting that as quotation marks. I'm going to get to that in just a second. So centripetal force, if you think of F equals ma, all right, if you're talking about a centripetal acceleration, well then that means that you're going to use a centripetal force. Okay, so if we kind of rewrite this, the centripetal force is equal to mass times the velocity squared divided by r. Okay, based off of our equation from last time. Now, here's where the quotation aspect is happening. All the other forces, you have those two objects because that's what happens. A force is the result of an interaction between two objects. With a force of gravity, it's the between the Earth and an object on the Earth. The tension is the force between a string and an object. The normal force is between the surface and an object, and so on. Spring force is between the spring and an object, right? So centripetal force isn't actually a force between two objects. Instead, centripetal force is a special kind of net force. All right, it's a special kind of net force. Most of the time, the sum of the forces, or the net force, is equal to mass times acceleration. But when you're talking about something that's moving in a circle, that net force is now equal to not just mass times acceleration, but mass times centripetal acceleration. And so when we refer to centripetal force, this is what we're referring to. A special kind of net force, right, that is equal to mass times the centripetal acceleration. So here is a couple of examples. Okay, so take a look over here at this picture on the right. You've got a car that is moving around a curve. Now, as that car is moving around a curve, it's at a constant speed. The friction that's keeping it directed toward the center, that is the net force that's going to be causing the quote-unquote centripetal force. Take a look here. So if we've got the normal force coming up, and we've got mass times gravity coming down, and then there's that frictional force is what's keeping it moving in a circle. So if you take the sum of the forces in the y direction, we know that the normal is going up, the mass times gravity is coming down, and that it's staying on the road, so there is no vertical acceleration. So we can just say that the normal force is equal to mass times gravity. On the x side, in the x direction, the sum of the forces in the x direction, well, the only force is equal to friction. That's very obviously not balanced, so it can't be zero. So it's, like I said, it's that friction force is what's keeping it moving in the circle, which means this is a case of centripetal force. So it becomes M like this. And we'd be able to solve that way. So basically what it's saying is, instead of saying, we also know friction is equal to this, so mu times the normal force, so we could solve for friction two ways. We could solve it using what we know about the normal force, and we could solve for it using what we know about centripetal acceleration. Let me give you another example. I'm going to kind of clear this page off. So this picture, you've got an object on a string. Class, I used a timer. And I'm going to swing this object in a circle. I'm not very good at drawing circles. Okay, so as this moves around the circle, there are two forces that are acting on it. Give me a second. Okay, there are two, as it's moving around the circle, there are two forces that are acting on it. Okay, let's do a free body diagram. Okay, there will always be the force of gravity pulling it down, and a tension force as well. And that tension force is what keeps it moving in a circle. So here's basically our tension right along the string. So let's say that we're talking about the string is at the top of the circle. All right, so we are right here. Here's our object, and it's moving around. So at that point, the weight force is going straight down. Okay, there's our weight force, and the tension is also pulling straight down. So in this case, the net force, all right, the net force is what is keeping it moving in a circle. So our net force is actually our centripetal force. So what we have here is we have tension plus the weight is equal to mass times our centripetal acceleration. Okay, so there we go. Let's do it another way. Let's take it if it was, say, at the bottom. Okay, now if it's at the bottom and moving through its swing, what happens is that we have the weight force acting on it down, but this time, all right, tension isn't acting down, it is acting up. It's pulling it towards the center. That's what centripetal means, center seeking. So weight comes down, the tension goes up. We write our equation, the sum of the forces is equal to mass times acceleration. All right, in this case, that force, the net force that is keeping it moving in a circle is our centripetal acceleration. I said that incorrectly, I apologize. In this case, the net force is a force that's keeping it moving in a circle. So that net force is our centripetal force, and that makes this our centripetal acceleration. So that just means we have the tension minus the weight, because they're going opposite, is equal to mass times acceleration centripetal. And in this case, we cannot say that these two things are equal. They are not equal, and we know that because it's moving in a circle. So to reiterate, centripetal force is a force that is always pointing towards the center, and it is a special kind of net force. Right? You will never ever You will never ever actually put a centripetal force onto a free body diagram, because the only thing that you put on a free body diagram are the forces that are the result of an interaction between two objects, and centripetal force is not that. Okay, so here's an example. We're going to go ahead and talk about the Earth and the Moon, and the Moon orbits the Earth at a distance of 384 times 10 to the 6th meters. We need to know what is the Moon's acceleration towards the Earth, how much does the Earth pull on the Moon, and does the Moon pull on the Earth more or less the same as the Earth pulls on it. So first off, there's a little bit of a typo in here. These are all exponents. There we go. All right, so let's take this and think of it like this. Here is our orbit of the Moon. Please also realize that this is a simplification. The Moon does not actually orbit us in a circle, in a perfect circle. So if this is the Earth, here is the Moon, and it's going around. Here's the radius. Okay, so the first thing, we're actually going to kind of approach this backwards. And that is, what is the force between those two objects? Okay, the name of the force, the net force that's acting in this scenario, so if our net force is equal to mass times acceleration, the force that is acting, that's keeping it moving in a circle, is only our force of gravity. So our gravitational force then is equal to mass times the centripetal acceleration, because that's what's keeping it moving in a circle. All right, so let's take a look. If we want to find force of gravity, we need to have mass, and yes, we have the mass. All right, I do not see centripetal acceleration anywhere on here, so we're going to break that down. So our centripetal acceleration is equal to v squared, velocity squared, divided by the radius. We have the radius, okay? Note that this radius is from the center of the Earth to the center of the Moon, okay? Not from surface to surface, center to center. So if we want to find, so we have that, so we still need to have our velocity. So velocity is basically a change in position divided by a change in time. So as the Moon orbits the Earth, the distance that orbit takes is considered, well, it's the circumference of that path. So it's 2 pi r. And again, we have r, so we're good. The other thing is, well, okay, how long does it take to do that? How long it takes is the period. The period is the amount of time it takes to complete one rotation. So it's 27.4 days. So from here, we can go ahead and do the math that's going to give us our velocity. So it's 2 pi times 384 times 10 to the 6th meters. We're going to divide that by the period, which is 27.4 days. We're going to convert that in. We know that there are 24 hours in every day. And in every hour, there are 3,600 seconds. Our hours cancel, our days cancel, we're left with seconds. We do the math, we end up with the velocity of the Moon orbiting the Earth is 1,019 meters per second. So now we have our velocity. We're going to come back over here and do some work. So we're going to take that velocity, and we're going to plug it into the centripetal acceleration right over here. So that means that we have 1,019 meters per second, and we're going to square that, and we're going to divide that by the radius, which was 384 meters, 384 times 10 to the 6th meters. If you do that, you end up with 0.0027 meters per second squared, and that's your first answer. Okay. Yeah. So we're going to use that value here that I just boxed, and we're going to use that in here to find the force of gravity of the Earth pulling on the Moon. So the force of the Earth pulling on the moon, Earth on moon, aka gravity, is going to be equal to the mass of the moon times the centripetal acceleration, which you just found. So we're looking at 7.35 times 10 to the 22nd kilograms times the acceleration is 0.0027 meters per second squared. And we end up with a gravitational force of 1.98 times 10 to the 20th newtons. There's our second answer. Our third answer asks, does the moon pull on the Earth more or less or the same as the Earth pulls on it? Well, the moon will pull on the Earth the same as the Earth pulls on the moon because of Newton's third law. All right, that's the gist of centripetal acceleration and centripetal force. See you tomorrow.